All right, so here is the, I think this will be the final video on Class 8. Let me turn the fan off. Background noise bothers me. Anyway, so we can also, in similar fashion to we derive from Bernoulli, we could also take a look instead of the streamline direction, the normal to the streamline direction. In that case, the acceleration that we're looking at becomes, let's see, can I write on this? Where's the thing to write on it? There you go, we can write on it here, sure. Then the acceleration is now the one that we expect from that we saw in dynamics, right, for the normal and tangential, right? So we could think of the S as being the tangential direction, and we could think of the normal as being just like the normal direction is pointed towards the center of curvature of the streamline right there, right? So we could do this formulation, and what we're really looking for is to find how the pressure gradient will vary across adjacent streamlines. And here is a slide. So that was a figure from Munson. Here's a figure from Sengel talking the same thing. So without having to go through the derivation, right here is what we end up with. By the way, a very common way to write out Bernoulli is to divide everything by the density right there. So you'll see that the density. One important thing that you might notice right here is that this part right here remains an integral. And that's one of the reasons why is we don't know how the velocity will depend. We don't know that it depends of the velocity or the radius on the normal right there. So in order to be able to integrate that, we have to have more information than we would want to make this a generic integration. That's what I'm saying right there. So here is an example. Ooh, that's a little out of focus. We have water in a container, and air, water in a container, and air in a tornado flow in the horizontal circular streamlines. We have radius r and velocity speed v, as shown. There's a video that we could probably watch of this, but we're not going to. Determine the radial pressure gradient. So here you go. This is the radial pressure gradient that we want out of this thing, needed for the following situations. Right. A, the fluid is water with a radius of 3 inches and a velocity of 0.8 feet per second, or the fluid is air with a radius of 300 feet and a velocity of 200 miles per hour. So let's take a look, and I don't think I have my camera on right now for some reason. Okay, let me get that camera on. No, I don't want that. I'll just escape out of this and show, discard, and there you go. There, camera. There you go. All right, so here we go. Where's that last sheet? I lost it. I must have moved this over here. This is going to be a great video. There you go. There, right there. Boom. So, I'm going to look up some material properties, or do I need them? I guess I already kind of have them, right? So I'm going to go for the A here. We're going to use the H2O, and we're going to say that it's 1.94 slugs per cubic foot. That's what we need right there. And using this equation that we just put up on the board there a second ago, we're going to treat the thing in the same plane. So that's going to go away, and we're going to be able to find, so we're going to treat this dn. So this is a different version of the thing. Here's what we want to try to find. We're going to try to find where that pressure gradient is, like that right there, compared to here. So that's actually what we're using. We're not using this equation. We're using the one before it gets integrated, and this one goes away because there's no change So here we're going to set that pressure gradient. We're going to say that, and they can be partials if they want to. It doesn't really matter to us. We're just going to say that these equal each other right there. So that's going to be over the radius. And so, you know, we're at this spot right here, but we're trying to find, you know, if we had rings, concentric rings of streamlines right here, we want to try to find how the pressure is varying with the radius. So that's what we mean by trying to find that del P del R. And then actually they're showing it as a del P del R, so that's fine with us, right? So really what we're having is 1.94. And the velocity here is 0.8 squared, and the radius is 3 inches, so we need to make it into feet, right? So that's all these units will work out to having a pressure gradient that's going to be 4.97. These are going to be pounds per cubic foot, right? Because it's pressure per foot is what we're finding the pressure per distance. So it's going to be pounds per square foot per foot, which comes out to pounds per cubic foot. So that's like the answer for this. And then looking at another situation, that's just going to be water in it's in a very small, like little, maybe it's what they say, it's water in a container, and maybe it's being drained out. Maybe that's, and so we're just looking at a spot away from the drain as it's trying to circle down. And here we're going to get the density of air for this, which is going to be 0.00238. So I'm using it out of this resource right here, right? So we're so there's 2.38 e to the minus 3, so that's the same thing that I just used. And we also need to take our velocity, which was at this guy 200 miles per hour, and we multiply by 5,280 and divide by 3,600, and we're left with 293. Might need another sig fig in there if we weren't going to be a little better than that. But anyway, we can plug this in and say we're going to have 0.00238 times our velocity squared, 293 squared, and divided by our radius, which we said was going to be 300 feet. So we end up with a pressure gradient of 0.681 pounds per cubic foot. And we can see that this is having the water is significantly more than than having the air in the tornado. So I think that's the takeaway from this. We don't really need to use this for much, but we might want to think about things in terms of what a pressure gradient, maybe the usefulness of it. And I don't know. I decided to be inclusive in here because this topic is shown in every textbook, and so we might as well work through a problem just to kind of see what we're talking about. Maybe it'll stick in your head better. That we can also do what essentially is Bernoulli across a streamline, but most of the time we just stick with along a streamline, and that's the main Bernoulli. So that's it for this video, just for completeness.